Okay, so here is something we've derived in the past. When we computed the velocity of any point, we wrote down the formula as j times q dot. Right, so this is the Cartesian velocity. And then this is the joint velocity. So in particular, if I give you the example of a two-link pendulum, then that's the velocity of the end effector. Let's call that E, like VE. And then Q dot is going to consist of two things. One is the rate at which this moves, so theta 1 dot, and the rate at which this moves, theta 2 dot. So Q dot is theta 1 dot, theta 2 dot. Okay, so let's see how we can use this to do inverse kinematics. That is, we want the point E to track some curve. Okay. So I'm going to take this equation and write it as d. Let's call it r. R being the position of point E, and I'm going to put well, dt is the rate of change with respect to time, j times dq dt. Just rewriting the whole thing. So VE here is clearly the rate of change of position of point E. So if you want, you can put RE in frame 0. Okay, so what we'll do is we'll get rid of the dt because there's a dt appearing on both sides. So DRE is equal to j times dq. Or in other words, if you want to find the rate of change of dq, it's j inverse DRE. Okay, so we are very close to figuring out how to do inverse kinematics with that formula. What I'm going to do is I'm going to write this right-hand side as j inverse. Okay, so what is DRE? That is basically the rate of change of position. And I'm going to assume that to be the reference minus the actual value. Okay, so what's those things? That is the reference position. So for example, if you're tracking a circle, you know what the reference is going to be. It's basically points on the circle. That is stored in RF. And then this is something which is measured. Okay, so assuming that you have a sensor, you can measure RE. Or what you could do is, if you know the joint angles, you know theta 1 and theta 2, you can use the forward kinematics to figure out what that position is. So either of those two will work. So what this does is it basically gives you the change in Q such that the thing on the right-hand side is you're attempting to make that go to 0, right? If that is 0, then the update dq is going to be 0. If that is non-zero, dq will change. So it's always dq is trying to change q such that ref minus re in frame 0 is 0. Let me just rewrite this expression. Okay, so we'll write it as the same thing, dq equals j inverse ref minus re 0. So what this would have in it is x ref, y ref, because position of anything on the point has two coordinates, x and y. RE is going to be the x, y coordinate. This is a measurement, and the Q is the update. So what you do is uh, to trace a reference, all you do is you update Q as Q plus DQ. So you start with one Q, you take the J inverse, you do the difference between RF and RE, pad that to DQ, change Q, and you keep doing that. So this is how you would basically update Q such that RF is always on RE. Okay, and we'll just understand how this works by looking at some code. Okay, so I'm going to try to get a two-link pendulum track a circle, and we'll use this formula to do tracking. Earlier, we had used fsolve to do tracking. So Q was computed using fsolve, which is using a nonlinear root finder. But this time, I'm going to use this formula. Okay, so it's drawing the circle, and those points are basically the reference. Here, I should have put a legend, but it's basically, I think you can check it here. It's randomized. Okay, close in just a bit. Oh no, okay. Okay, so we can check what blue and red is. If you go here, plot, not this one. Oh yeah, this one. Blue and red. Red seems to be the reference, and then the blue seems to be this. So I think a better way to write this is you probably want to have a solid line for the reference. So I think this is better, and then you can put. Okay, so let's see. So this is basically about 130 lines of code. And to break it down, this is essentially taking some of the code which we wrote for the forward kinematics and inverse kinematics, except that I've replaced fsolve with something different. So Jacobian of point E, that is a formula we derived some time back. The forward kinematics comes from some of the earlier code. There's nothing new here. It basically uses the homogeneous transformations H0 and H12, and it eventually outputs the position of point P and Q, P being the end effector, sorry, Q being the end effector. Okay, and so it returns OP, actually returns the origin, which is 0, 0, P, which is the elbow, O is the shoulder, P is the elbow, and Q is the hand. So length is 1. I give an initial guess of this is the equation of a circle, x ref, y ref. That's I wanted to plot, go on that circle. And then see, so compute the Jacobian, compute the inverse, because I'll need that. Do forward kinematics. This is just to compute x and y, and this is what I put down. Well, this is just giving the difference, but this is exactly what I wrote down. Okay, there's two lines. I split them into two lines. So I compute dx, x being capital here, is basically the reference minus x. So x ref minus x, y ref minus f, the error between the actual needed trajectory reference and the x and y, what actually it is plotting, and then do J inverse dx. So that gives me the change in Q. And then I just update theta 1, theta 2. So this plus equals means it's theta 1 equals theta 1 plus dq0. Okay, and I just save that. That's pretty much it. Another way of doing inverse kinematics using the Jacobian. Okay. Now there is a problem though. If you see here, see the red line. It basically is it's closed. The blue line is. Let me increase this pause. So there's a problem with the tracking. If you see the tracking, it doesn't really complete the whole circle. So the blue is the one you need to look at. The blue is dashed line. So you can see it stops here, starts the right place, but stops here. It does an error. Okay, so it's not doing a perfect tracking. It's actually stopping short of the complete circle, and that's because what happens here is I don't do any error correction. So I basically use this formula to figure out dq, but the dx may not be equal to 0 because it's just using that formula doesn't ensure that dx is 0. Ideally, I would like to have dx 0 at every point, right? Because dx is basically giving you the error. So one way of fixing this, and I've not done this here, is to keep doing this particular update a few more times till dx is close to 0. So that becomes like f solve, where you don't really let it move forward unless it makes the right correction. So you could basically write a for loop or a while loop, have some tolerance on dx so that the error goes to 0, and then proceed to the next iteration and so on. So um, it has some problems, but can be easily fixed. Okay, so then it becomes like f solve, but I think it can be much faster because of the way I've done it. It's like you have full control over how you manipulate dq. You could specify whatever tolerance you want, 1e negative 3, or sometimes you don't care about being very accurate and you can keep it 0.1, 0.01. Okay, so that's how you would do it without using fsolve. And this is how people would do it if they care about implementing on, let's say, a system where computing is scarce. Let's say you're using Arduino to do this, then you would probably not use fsolve because that'll take a lot of time. So you probably use this. The other problem is these computations have to be done really quickly. Imagine this manipulator is trying to do this computation to go and fetch something. In that case, you again want to do something which is quick, not as accurate, right? Because you want it to be done. And so you might want to use something like this. So both fsolve and this method has its own advantages. This method is called inverse kinematics using differential kinematics. So differential kinematics, because you use Jacobian. Jacobian is basically the rate of change of uh, x. So that differential is because of that rate of change. J uses the rate of change. And that's why if you hear ik with, I'll write it here, ik with differential kinematics, they're talking about using J inverse in this form. Okay, now there's another problem here, which you might, I don't know if you noticed this, but this only works if J inverse is not, well, the determinant of J inverse is not 0, right? So there are cases where the J inverse would be 0. An example would be if you take the manipulator and you make, if you make the arm straight, that is the angle theta 2 is 0, then J inverse will actually be um, the determinant of J would be 0. And if the determinant of J is 0, you cannot find the inverse, and this will fail. So if you might hear something if you talk with people about singularity. So singularity happens when the determinant of J becomes equal to 0. So you never ever want to have a singular configuration. In fact, if you try to start doing this computation when theta 2 is equal to 0, J would actually, this will never fail. So if you go back here and if you look at this Jacobian and you try to compute its inverse, when theta 2 is equal to 0, you'll see that it actually comes out to be not defined. Okay, so this should be beware of. Avoid singular configurations.